Hello everybody, welcome back to Munro Live. I'm Tom Prochet, Director of Electrification for Munro Associates. If you don't know who we are a lean design, lean manufacturing consultancy. We're kind of notorious for doing teardowns of electric vehicle related technologies, cost reduction, but truth be known, we're also really big on engineering projects and doing things that are unique to specific clients. So today we're going to talk a little bit about battery cooling. And I mean both battery cells and the battery pack itself and the differences that play into that, especially including the module that's the sort of intermediate step between the cell and the pack.
Hey everybody, Munro Live is brought to you today by Babbel. Babbel is one of the top language learning apps in the world, and it's scientifically proven to help you learn a new language in just 3 weeks. I travel a lot in my line of work. No matter where I am in the world, I like to greet people in their native language and connect with local cultures through communications. Guten Tag. Mein Name ist Sandy. Wie geht's Ihnen? I've decided to make Babbel a must-have for me when I'm on the go. Babbel's lessons are crafted by more than 650 language teachers. It has dedicated courses to help me focus exactly on what I need to say when I'm traveling abroad. Enchanté. Je m'appelle Sandy. Merci beaucoup. You can even learn in the form of podcasts, games, and live classes with real language teachers. Click the link in the description and get 60% off your Babbel subscription. Please let us know in the comments what language you decided to learn.
So let's start with some pretty fundamental aspects. There's 3 types of thermal heat transfer that you should probably be aware of as, fundamentals of physics, if you will. There's thermal conductivity of a material. This is like a heat sink. If you've ever seen a heat sink, an electronic component gets hot, it's attached mechanically to a large piece of metal that the difference in temperature across that piece of metal carries the heat across and away from the part you're trying to cool. So that's conductive. It's all about the material and what its thermal properties are and how well it does its job at cooling. Then there's another one that's a little bit more difficult to understand that's called convection. So this is where there's some sort of a fluid involved, and when you say a fluid, I don't mean necessarily like ethylene glycol or water. Air is also a fluid. The basic idea here is that we can transfer heat between 2 different devices with this fluid medium. And then there's another one called radiant heat. This is one where there doesn't need to be a fluid or any sort of coupling at all, because it can through a wave, it can transfer the heat. And this is analogous to the way the sun heats the earth. The space is a vacuum, there's no real fluid in between there, yet the sun manages to heat the earth quite well. So with those basic fundamentals, what we find in batteries is some combination of these 3, typically a combination of the first 2, and I'm going to get into some detail about what that means. So first and foremost, you have to be able to characterize a material for its thermal conductivity. This should not be confused with what would be its thermal impedance, which is the opposite. So conductivity means its acceptance of that heat and its ability to transfer the heat. An impedance would be the opposite, or its ability to isolate the heat or keep it from transferring. So the materials we will look at will be either rated as a thermal conductivity or as a thermal impedance. And it's really kind of a function of what the material is. If you're looking up the material as what we call a thermal interface material, or TIM as it's called in the business, then generally speaking, it's about how thick it's going to be in the end. The thicker it's going to be, the more you want to talk about thermal conductivity, because that thickness is really important, as we'll talk about. The thinner it is, and the more under pressure it might be, the more we might talk in terms of thermal impedance. So the one that most people are familiar with for thermal conductivity is watts per meter Kelvin. So basically the idea here is a big number is good for thermal conductivity, a smaller number not so good. The per meter Kelvin part of it is your clue that the thickness is important. So use a high K factor, which would be the number that we're talking about where bigger is better, and use it as thin as possible to get the job done. So in batteries, we don't always get the luxury of doing that, and I'll try to explain some differences as I show you the different examples. So let's start with how we might cool a cell of a different type or another. We have a couple of different cells we can look at here, and I'll give you some good examples. So we're probably mostly familiar with the cylindrical. This is what Tesla uses, this is what Lucid uses, this is what Rivian uses. There are different shapes and sizes. We have different form factors, we call them, that represent their lengths and their diameters. And in this case, this is a 4680 Gen 1 from the first Model Y structural pack that we took apart. There's a Model S cell, which is the smallest of all of them. That's an 18650, 18 millimeters in diameter, 65 millimeters in length. And then there are the 2170s, which round out the rest of what you see here. So the basic idea is it's a metal can. Inside there's a jelly roll that's got the anode and the cathode and the separator and the electrolyte. And that's all very similar no matter what type of battery we're talking about. That could be the same for a pouch or for what we call a prismatic. So the way I like to look at the pouch is what's the least expensive way I can do this. And the way I do that is I use a plastic envelope and I put my jelly roll inside there, and it's very inexpensive. It flexes, it moves all over the place, it grows, it expands and it contracts. This would be something where it grows during charge and it contracts during discharge, and it also grows over the useful life of the cell. So it gets ever bigger as life goes on. So that presents a particular problem to a thermal interface material because it has to be flexible. As this thing blows up like a balloon and contracts again, even though you can barely see it with a naked eye, it's enough of a movement where the thermal interface material has to remain pliable or compliant to the change in mechanical shape of the cell. Now, if you take the pouch cell and you put it inside a metal can, you basically have the makings of a prismatic cell. So this is metal. There's a jelly roll inside there, or 2 or 5. It doesn't really matter for our discussion. But I have the ability to extract heat from the bottom, from the side, or the edge with this one. Whereas with the pouches, we've had myriad ways this has been done in the past, and I'll just show you an example of some of them. So back when I first got into this business, the Chevy Volt with a V was very popular. I don't have one of those handy to show you, but I can show you what it kind of evolved into. The Volt with a V had a metal plate sort of like this. You can see this plate. This is touching up against the battery cell. There's another battery cell on this side typically. So two cells share a common aluminum plate. The heat transfers down across this surface area, comes out the bottom of the plate, and this little L-shaped bracket is where the heat is taken away from using a cold plate device, which is a heat exchanger that removes the heat. So I generate the heat inside the cell. I take the heat away along this aluminum material. This works pretty well, except it's expensive. The predecessor to this worked, I would argue, even better, but it was even more expensive. And what they did in that case is they actually put coolant lines in here and had to provide plumbing that fed ethylene glycol as a coolant to be able to take the heat away using liquid. And while that worked really well, it was really expensive and wasn't very popular for very long. So the Bolt with a B kind of dropped that concept of the coolant and went to the solid plate idea. And then as time went on, it became obvious that even that was too expensive. So the most modern way we see it done is really quite simple. And that is you take the bottom of the cell and they use a thermal interface material along the bottom edge. So again, this expands and contracts, so it's got to remain somewhat pliable to be able to accommodate that. But all of the heat is taken away off the edge. So no longer are we trying to take heat away from the surface area. The reason this works is that when you go inside the jelly roll, you can actually see that the bottom edges of the anodes and cathodes are all exposed along this length in such a way where the heat can travel down those anode and cathode materials. This is copper and aluminum typically. And that material moves the heat quite nicely right out to the edge where it's taken away along the bottom with a little bit of tin. Now that said, that doesn't work very well when the cell gets tall, because now I'm trying to take heat generated way out here and move it all the way along the length of the surface area out to the very bottom where it comes out. So it works really well on these sort of candy bar shaped pouch cells. It doesn't work so well when the cell becomes square shaped or a little bit wider in the rectangular shape. So that said, we've seen now clearly 3 different ways you can cool a pouch cell. And you can also see the analogy of how much simpler it is here. I have options. This still expands and contracts a little bit, so you do still need to manage the compression of an array of these things, but nowhere near to the extent that you have to with a pouch. But you do end up with this flexibility on all these different metal surfaces from which I can extract heat energy. That being the case, let's take a look at the cylinders that are something quite popular around here at Munro Associates. A lot of people wonder about that popularity. We have a lot of experience with the Tesla stuff. They've never been our customer. They have a rather unique way they do things that represents some evolution from when they first got in the business to where they are now. And what I want to do is kind of show you that. I walked you through the evolution of the pouch cell cooling, and that's pretty much the way it is across the board amongst all the pouch users. Tesla has a kind of unique history with what they've done with their cylinders dating back to the early Model S. I don't have any firsthand knowledge of what it was like in the Roadster, but I do have a Model X module over here that you can see. It's a 2017 vintage. Sitting right next to it is the Model S 2018. The S and the X share a platform, so their modules are very similar to one another. They're arguably interchangeable. It's the same battery pack type, if you will. So that being the case, these modules, when you look at them, they appear to be interchangeable. And they are more or less interchangeable from a mechanical form factor standpoint. They have the same length, width, and height as each other. They have coolant ports on one end, both of them do. The cooling pipes themselves are somewhat different, and that's the part I wanted to mention here. So if you look at this one, it's kind of hard to tell, but I'm guessing we can get a good camera shot in on it. You see 2 columns of cells running longitudinally, along with a little blank spot with 2 more columns of cells, another blank spot, 2 more columns of cell, blank, 2 cells, blank, all the way across. The reason that you've got this little blank spot in there is in the middle of that, there's a cooling pipe that's straight. So it has thickness, and it has to run down that longitudinal stretch, touching the tangents of each cell. So if I go back to the analogy of the cell, that would be, I'm picking up just the very edge of that cell as a tangent. You can see it's not a very wide angular range that I'm covering, it's just the tangent. So I have some thermal interface material in there, and maybe I can pick up a little bit more surface area because of that, but I'm still just cooling the side of the cell as a tangent. Now, enter what the change was that occurred this 2018 vintage. The first thing you notice is that when you look at the cell array, there's 2 rows of cells, 2 more rows of cells, and whoa, wait a minute, they're all equidistant from one another. No longer do I have this gap in between them. That's because the coolant pipe on this one has a serpentine effect. It fishes its way through the cells in an S shape, if you will, what we call a serpentine cooler. So that allows the spacing between the cells to be closer together. And because I did that, I can actually fit more cells in this one than I can in that one. So I've inadvertently increased the energy content of the module, as we call this, and simultaneously improved its cooling by a rather significant amount. And I'll explain another reason why that's the case. If you look at the Model X, you can see there's a single coolant inlet and a single coolant outlet. I don't know which one's which, doesn't matter. Coolant goes in here, comes out there. If it's cold water coming in, these cells are nice and cool, and they get warmer and warmer as they go through this whole thing. There's a temperature gradient that occurs along the length of this cooling pipe, where at the outlet, I've got hot water coming out, and these cells are much, much hotter than the ones that are being cooled with the cold water at the inlet. So the very first thing they did was they split that into 2 different loops. Now, while I still have that same sort of temperature gradient from this inlet to that outlet, I've cut the problem in half. I have a separate inlet for the second half of the module, So that particular problem where there's a temperature gradient along the length of the cooling pipe, that's been cut in half. Then you add to that the fact that I'm now picking up a much greater angular range of the side of the cell. It's no longer a tangent. I can get somewhere probably between maybe 40 and 70 degrees of the angular surface of that cell touching up against the side of the serpentine cooler. Let's take a look at one of these serpentine coolers. See if I can reach it here. So this is the one out of the Model Y structural pack. You can see the way they've constructed this thing is rather unique. It's got several passages inside it that are, sort of autonomous. They create a path for flow that's laminar. So if I flow some fluid down one of these little individual tubes, and I flow the same amount in all the other individual tubes, they all flow about the same along the length. Now, if I just made that one big open passageway, I might try to flow in at one side and it kind of finds its own way through there. This is a much better way to make sure that the coolant stays consistent in its flow across that surface area of the cell where we're touching up against the side. So now this has to be electrically insulating because the cells are typically at different voltage potentials. So if I had it electrically conductive as the natural aluminum would be in the raw form, then I'd be shorting out all the cells along the length of this. So we can't do that. So there's this coating over the top of the cooler that represents an electrically isolating thermally conductive material, a tin, if you will. And they've further taken this concept down another path here that I want to show you. So very clearly we have an inlet and an outlet, but on the Model Y structural pack, what we found was that the inlet and the outlet were on the same end. We saw that previously on the Model S. So if you can zoom in on the dark blue module over there, you'll see that the end of that module has both a coolant inlet and a coolant outlet on the same end of the module. Whereas right next to it in the light blue, the previous Model Y, that had a single inlet on one end and the far end had the single outlet. So we still had the big bad temperature gradient across the light blue one, but the dark blue one, that serpentine cooler would flow coolant down one half of the pipe, go to the very end of the module, go into a little bulkhead, turn around, come back where it came from down the other half of the cooling pipe, and allowing the inlet and the outlet to be on the same end. Now, call it the top side of the cell, gets the cold water, and it gets progressively hotter as it goes down the length, turns back, comes back around, still getting hotter, but now I'm on the opposite side of the cell. So every cell gets a little bit of cold, a little bit of hot, and the temperature gradient all but completely disappears. So they've taken that to a new level with the Model Y structural pack. This is the cooler from that. It's much bigger, and it sort of typifies the way they do business now. The same one-ended coolant connections so that this pipe has both inlets flowing cold water in, goes all the way down to the end, turns around, comes back, getting hotter and hotter and hotter, and there's the outlet where the hot water comes out. So again, this cell here is getting a little bit of cold and a little bit of hot. This one down here, it's pretty much got warm on both its top and its bottom. So again, they've worked quickly to try to iterate and get to a system that gives them good thermal performance and minimizes this whole temperature gradient that's a natural phenomenon. Whenever I try to cool something down with cold water, I can't do it uniformly because, computational fluid dynamics make that difficult. So let's look at the way some of the others have done it. This kind of shows you that Tesla has gone through a mile of broken glass to get where they are today. And, their system that we consider their state-of-the-art now wasn't always that way, and it wasn't very long ago that it wasn't anywhere near as good. So that said, let's take a look at the way Lucid did things. Lucid has a video that talks about bottom cooling of their 2170 cells. So this happens to be out of a Lucid module, and you can see all the 2170 cells. They're still sort of in their original positions here. You can look at the very bottom of the cell and you can see that it's got a very flat sort of epoxy-like surface on it. This is a glue that's very highly thermally conductive as it takes the heat away from the bottom of the cell and into what is the cold plate down below it. So this, of course, originally was mated as such, and they were very smart about it. You can see that there's a very, very thin bond line. This material is as thin as they could make it, because we talked early on about how thermal interface materials are best with a high K factor. Big numbers are better, but it's also best to make it as thin as possible so that it doesn't represent any sort of real impedance to the thermal conductivity. So on the cooler side, there's a very thin sort of membrane, again, electrically insulating, thermally conductive, but also very, very thin. So when you consider what they did on the far opposite end of the spectrum, jumping around a bit here, but back to the pouch cells of the Ioniq 5, there's a thermal interface material inside this thing that's that thick. So not only are we picking up the edges of the cells, you can see where that thermal interface material was, and we've just kind of plucked it out of there and left a piece of it for show and tell here. But the idea is that not only am I grabbing the edge of the cell, which isn't necessarily ideal, especially if this is a real deep cell, but it's also very thick. So the thermal conductivity of this material is really important, but the fact that it's so thick kind of works against that. And they're not really trying to extract heat out in any sort of quick way. How do I mean by that? So we have continuous power performance that we need to be able to drive down the road at a steady state speed. Every vehicle requires a certain amount of power as a function of its rolling resistance, its aerodynamic drag coefficient, and its frontal area. And you can know pretty precisely how much power it takes to go at a steady state speed. And once you're in that mode, it's all about the continuous performance of the cells. How can I continuously extract heat to keep them at their ideal operating temperature? When I put my foot into the throttle, now suddenly the current goes up, I'm delivering a lot more power, I'm making a lot more heat. Can I design a cooling system that helps me take that heat away in a short period of time? If I can do that, I can achieve a higher level of power performance from the cells within that pack module or the individual cell itself. The basic idea here is that if I can create a very dynamically behaving cooling system, then I can get a little bit more power performance out of it. I can accelerate better as a function of that better power performance. This may also work the same in regenerative braking as I'm trying to charge the battery with kinetic energy of the vehicle slowing down. Same analogy here, but the basic idea is that in this one here, this is probably more about steady state operation and taking the heat away and keeping the cells at a comfortable temperature under the normal use of the vehicle, even when going up a long grade and maybe pulling a small trailer. Whereas in the case of the Model S, we know that they had insane and ludicrous modes before there was ever a Plaid, and power performance was really, really important. So Tesla was able to create a system where they could extract heat out of the cell really, really nicely. And this is one of the reasons why the king of the hill for power performance at Tesla is the smallest cell in the group. It's got what I would call a high surface area to power ratio. It's a pretty small cell. It's got lots of surface area to grab heat from, and there's lots of cells to work with. So they're able to pull heat out of this in a way that's short-term meaningful so that I can get really fast bursts of high power out of this battery pack. So again, cells, modules, packs, we'll talk about how that works at the pack level at the end here. So looking closer at other ways it's done, here's a pouch cell pack, or module I should say, from the Ford Lightning. You'll find that there's a cooling plate at the bottom, or cold plate as we like to call it in the business. There's a plumbing inlet there, a plumbing outlet there, or it could be vice versa, I wouldn't know. But the basic idea is that, yes, inside here I've got a stack of pouch cells. They're stacked like pancakes along that length. And the bottom edge has some thermal interface material that sort of pokes through the bottom of the module and ultimately gets us coupled into this cold plate, where we use convection to use a fluid like water, but it's more of an ethylene glycol-based fluid, so that it has both anti-freeze protection as well as anti-corrosion characteristics. Anyway, the bottom line is that I will take the heat away from the bottoms of those cells and send it up to a radiator or some other heat exchanger that takes the heat away and dumps it back into the environment. And there's lots of ways of doing that. So you get to see the contrast in the different cooling. You've got Ford Lightning with edge cooling. You've got Lucid Air with bottom cooling with a very thin membrane. You know, by the way, I haven't seen the Sapphire, but it's now the new king of the hill apparently, having bested the Model S Plaid from an acceleration performance standpoint. If they've used the same design on the Sapphire, then it seems quite obvious to me why it works so well. They've managed to use a very thin thermal interface material with very high thermal conductivity for all the components, while maintaining the electrical isolation that's necessary so that these groups of cells don't short out against each other electrically. All right, so Rivian, I can show you, but I'll more easily just explain it. They also do bottom cooling, but what they do is instead of having a one-sided cooler like this is, and you can see some details of this cooler, it's kind of mangled after having been extracted, but if, for example, this is the inlet and this is the outlet, notice the tortuous path that the coolant has to take to go all the way down to the end, come back around, and come out the other side. This is very analogous to what Tesla does with their serpentine cooler. However, you can see these details are what they figured out during their computational fluid dynamics exercise. It's what they had to do to create a uniform or laminar flow along this area here so that they had uniform temperature across all the different cells that this is trying to cool. Rivian did a similar thing, only it's a two-sided cooler, and they can cool the bottoms of cells on both sides of the cooler, and you know, it's still taking advantage of the bottom of the cell being at a thermal advantage based on what Lucid talks about in their videos on the subject. So let's talk a little bit about that. If I take their 2170 cell and I cool it from the bottom, I have a certain amount of surface area that I can work with, and it's kind of smallish. If I cool it from the side with the serpentine cooler, you can see quite obviously I get quite a lot more surface area that I can attach to. But what's unique about the bottom of the cell is that it is ideally suited for extracting the heat. It's where the anode is. There's a tab inside there that's sort of a bottleneck that gets hot because it's a restrictor for current. So there's lots of electrochemical reasons why the bottom might be a better place to cool from. I quite like to talk about the Hyundai Ioniq 5. So it's all aluminum, and they've taken the cold plate and they've made it a singular unit. It is the bottom of the enclosure. So when they drop the modules in there, we're sitting right on the cold plate. So that's a pretty efficient design, with the downside being the fact that now I've got all this aluminum that's very highly thermally conductive. What does that do in terms of thermal runaway risk mitigation? Is that a good thing or is it a bad thing? Is it better to have a thermal insulator on the bottom? Ambient temperatures get into play there. For example, if it's really, really cold outside and I'm trying to heat up the battery and this bottom aluminum plate is sitting in ambient air temperature that's really, really cold, it's working against my ability to try to heat up those cells. If I have something insulating thermally at the bottom of the pack, that dynamic changes. For example, this Rivian pack that you see here has a composite bottom that is, by obvious appearance, you can't see it here, but it is a thermal insulator, and it is one of the things that isolates the ambient environment influence from the performance of the modules within the pack. So clearly different ways of doing things. What's best is not something I'm going to weigh in on. It is a subject of a very deep dive into computational fluid dynamics to be able to understand that. So there you have what is two contrasting ways of doing the same sort of thing. Rivian having this modular approach where there's individual cold plates inside that are all plumbed together, as opposed to one big giant cold plate where it's uniformly distributing coolant throughout the entire bottom of the pack. So over here you have what was the pack from the Lightning, and it had its own individual cold plates inside there too. I won't try to show you that, but the basic idea is it's very similar to Rivian in that I have individual cold plates per module, and I plumb them together in an arrangement that cools the pack nicely. So there you have 3 different approaches. You'll notice that this one even has a sort of plastic top. So it's one of the few that we find that has that. One of the reasons for that is that it doesn't need to provide shielding as much because the bottom of the truck is a sheet metal floor, and it provides that metal isolation that might otherwise be used or be accomplished with the lid being made out of an electrically conductive material. So they can make this electrically conductive with additives in the plastic or with an after process that sort of plates it. But it is an attempt to reduce the weight, and it works pretty well. So I thought I'd mention the fact that as we go forward, we're going to see more and more composite materials because they provide this thermal isolation from the ambient environment. We mentioned that we had that on the bottom of the Rivian. We have an elaborate arrangement I'll show in the next view of where we see this going in the future with using composite materials for the entire enclosure. Again, electromagnetic compliance concerns notwithstanding, there are other ways to manage that. This is about thermal runaway risk mitigation. This is about lowering cost. This is about that thermal isolation from the ambient environment. These are all good things to consider, but what I've hoped to accomplish here today is just to show the myriad ways this is done, and that it's quite a bit more complicated than what meets the eye. And if you're considering your own or reusing something from another application, these are all things that you need to take into consideration. And with that, I'll close with a look at this composite pack that we sort of created as a concept to show originally how much energy we could fit into a pack like that using the 4680 cells, and ultimately how the cooling channels can be integrated into the plastic itself. So if you follow me over there, we can wrap this up. So here you have the concept we're referring to here. This is a depiction of a battery tray, as we'd like to call it, that is made of a composite material, where that material itself can have designer elements to it that relate to its thermal conductivity, its ability to minimize radiation and susceptibility with electronic components, lower cost, and really one of the operative concerns about lowering cost is I can actually integrate the cold plate into the design as part of the design. So this is what we've shown to depict that. These are the depictions of the cooling channels and how they may route underneath the entire array of battery cells. And in this case, we've chosen an array of mocked up 4680 cells. These are all just wood blocks painted silver that gave us an idea how much energy you could fit in a given cavity. This was long before we ever got to take one apart and see what it actually did in the real world. So this is just a mock-up. It shows whether it's a cell to pack configuration, which this is depicting, or as we saw with the previous examples, it's usually, or most commonly, cell to module, then module to pack. So we're trying to show modules here as an alternative way. It doesn't really matter whether it's cell to pack or cell to module to pack, same basic rules apply. So you'll see a lot more of this in the future, and Munro's a big promoter of that sort of innovation. So last thing to close this out, there is a technology that you may have seen in other places that is called a heat pipe. So this is where you take a solid conductor like aluminum or copper, or maybe a combination of the two, and then there's a fluid medium inside it that goes through a vapor phase transition. So it's liquid when it's cool, but when it gets hot, it vaporizes. That should sound familiar to a lot of people because that's what water does. Water has 2 designer phase changes that are really helpful. One's at 100 degrees C, 212 degrees Fahrenheit. This is the boiling point. This is the vapor phase transition where it goes from a liquid into a vapor or gas. Likewise, we have another designer switch point called the freezing point, where at 32 degrees Fahrenheit, 0 degrees C, we transition from a liquid into a solid, or back and forth again. Now, what's unique about these transition points is that if I take a glass of water and I fill it with ice and I put a thermometer in there, that ice will put the water at 0 degrees C until all the ice is gone, at which point the water temperature will start to rise. So what I've done by using that particular phase transition is I've regulated the fluid temperature at or around freezing, and I keep it there until it's completely absorbed all the heat energy. Take the same vapor phase on the other end, and I can boil water, put a thermometer in it, and there it is, sitting there, stuck at 100 degrees C until all the water's gone, at which point the pot that I was using to boil the water that's now gone can suddenly rise above 100 degrees C. So again, I've used this vapor phase transition to regulate the fluid temperature, and I can do that with other fluids. They all have different characteristics. There are different materials that can do this. You may have heard of the term phase change materials. The basic idea is the same. Pick your temperature, design the materials around that temperature, and now I can regulate at or around that temperature using the phase transitions that are inherent to those materials. So we don't see it much in automotive, but their cold pipe, as you might call it, can also be a vapor chamber, where the cold pipe's usually sort of a unidirectional device. I move heat in one spot, it vaporizes, the vapor moves to another spot, it condenses in the cold spot, and that process repeats, but it is a unidirectional flow. If I have a vapor chamber, I can have a bidirectional flow, and it can be not just in a straight line, but across a big surface area. So if we had the perfect world with a big budget, we might be able to use these devices in our batteries. And if you were making a car that you really wanted to pay attention to the power performance of the pack, this might be one of the considerations you'd make. So again, in automotive, it's really all about how do you do it inexpensively, and it is what drives most of the decisions. The exceptions are when suddenly the vehicle also has to be able to do wild feats of acceleration performance, like the Lucid Air Sapphire or the Tesla Model S Plaid. This is where paying attention to those details can pay big dividends, allowing you to get big power performance out of the battery pack for a period of 10 seconds or longer, as it takes to get through whatever your motorsports situation is, whether it's a top speed run, a quarter mile, 0 to 60, whatever it is. You're going to want to design a cooling system that helps you keep the coolant level, coolant temperature down, so that the cell temperatures can be down, and again, your cooling system is going to be what gives you that ability. With that, I've given you enough to think about for one session here. Stay tuned for the next one as part of a continuing saga of battery evolution and how it relates to you in your life. Thank you for your time.